The universe probably started with a gigantic explosion. The remains of this explosion, the gases, hydrogen and helium, spread outwards through space. And from these thin gases, the stars were formed. In clusters, galaxies. Most of the universe is still made up of hydrogen and helium. Even stars, and at their centres remarkable things happen. It's hot, millions of degrees, and at those temperatures the hydrogen and helium get changed into other substances such as calcium, iron, titanium, copper, carbon and so on. But from the chemistry point of view, stars still aren't very interesting. These other substances are only present in tiny amounts. But the Earth is different. Very little hydrogen and helium here. The Earth is mostly oxygen and silicon. So something different must have happened when the Earth was formed, and must have been happening since. Many of the substances we know today are the result of countless natural chemical reactions. And today there's another factor at work, us. In the last few hundred years, we've discovered and made large numbers of new substances. The range of substances on Earth is vast, from those which make up the rarest gems to the abundant sand of vast deserts. From the materials of modern technology to the substances of life itself. And throughout history, people have tried to make sense of this bewildering variety. The ancient Greeks thought that everything could be made from just 4 basic substances, elements. These were thought to be earth, air, fire and water in various combinations. We no longer believe in that idea, but there is a grain of truth in it. Most substances are made up from simpler ones. Some substances are special. They can't be split up into anything simpler. By the 17th century, scientists realized that it was impossible to change these special substances into anything simpler. Mind you, that wasn't for want of trying. For centuries, the alchemists have dreamt of turning lead into gold. A lot of time and effort went into countless experiments. The alchemists hoped to get rich quick. But gold is an element. It couldn't be broken down or changed. Not even by magic spells and bubbling pots. Scientists borrowed the old Greek word elements for these special substances. By the beginning of the 19th century, over 50 elements had been discovered and identified. As the list grew, so chemists began to feel entangled in a thickening jungle. Each element behaved differently. Chemists could see no underlying pattern, and they despaired of ever finding one. It was a sort of giant jigsaw puzzle, but without a picture of what it should look like. The problem was how to sort out the pieces in a sensible way. And to make matters worse, some of the pieces were missing, and others weren't quite as they should be. The first key to a pattern for the elements turned out to be the idea of atomic mass. An English chemist called John Dalton had suggested that everything is made up of atoms, and that all the atoms of any one element were the same. And yet elements were different. Dalton had to imagine that all the atoms of one element were different from all the atoms of another. For instance, the atoms could have different sizes and masses. From their theories and investigations, scientists started to work out numbers which compared the mass of the atoms of one element with those of another. They called the numbers the atomic masses of the elements. This list was used in 1829 by a German chemist, Johann Wolfgang Dobereiner, to make a real breakthrough, though no one realized it at the time. Dobereiner knew that the metals calcium, strontium and barium behaved in very similar ways, For instance, they all burn in a hot flame with characteristic bright colours. They're often used in fireworks. Dobereiner was intrigued by their atomic masses. The atomic mass of strontium is roughly the average of the other two. The discovery of bromine in 1826 clinched things for Dobereiner. Bromine fitted in nicely between two known elements. Dobereiner called these relationships triads. Unfortunately, at that time there were no other clear-cut cases, so triads were shrugged off as interesting coincidences of no real value. The next important advance was made in 1864 by John Newlands, an English chemist working for a sugar factory. By then, 63 elements were known. Newlands arranged them in order of atomic mass. And he made a remarkable discovery: the regular recurrence of similar chemical properties. For instance, lithium and sodium are similar. They're both soft metals. This is lithium. And this is sodium. And they both react with water. First lithium, then sodium. Also, beryllium and magnesium have similar chemistry, and so on. But success was short-lived. For instance, take copper. Newlands put it in the same group as lithium, sodium and potassium, and yet chemically there's little similarity. Lithium, sodium and potassium all react readily with water. Copper doesn't. In fact, the pattern only worked for the first 15 or so of the known elements. After that, there seemed to be no pattern at all in the chemistry. Other scientists scoffed and suggested that Newlands might get better results if he listed the elements in alphabetical order. And yet Newlands was on the right track, if only he'd arranged his table slightly differently. The real breakthrough came a few years later, in 1869, when the Russian chemist Dmitry Ivanovich Mendeleev made two important improvements. First, although his table was mainly arranged in order of atomic mass, he wasn't afraid to change the order slightly to fit the chemistry. For instance, he swapped the order of iodine and tellurium. That made much more sense. Elements with the same chemistry now occurred underneath each other. Iodine with fluorine, chlorine and bromine. Lithium, sodium and potassium in the same column. And so on. But Mendeleev's real success came when he realized that there might be elements which hadn't yet been discovered. To his mind, the obvious thing to do was to leave gaps in the table. Mendeleev was so confident about his table, he felt that he could use it to predict the properties of the missing elements. For instance, in this gap, Mendeleev said the element would have these properties, amongst others. He called the undiscovered element ecosilicon. His fellow scientists were sceptical. They thought it was just wishful thinking. But then in 1885, germanium was discovered. Germanium exactly fitted the properties predicted by Mendeleev. Mendeleev was completely vindicated in the most dramatic manner possible. Now nobody had any doubts about the table. Well, no serious doubts, but there was still the nagging worry that Mendeleev had needed to ignore the atomic mass order in some cases. The problem was eventually cleared up by the brilliant English scientist Henry Moseley at the beginning of this century. Moseley knew that in certain circumstances, elements could be made to give out X-rays. Moseley realized that the different X-ray frequencies for each element indicated special differences in the inside of the atoms. From this, he was able to give each element a special number called the atomic number. And suddenly, things fitted into place. A smooth increase in atomic number. It's the atomic number that fixes the position of the element not the atomic mass. Even the tellurium and iodine type problems were solved. They are in the correct position according to their atomic numbers. At last, scientists had a table that worked, and they knew why it worked. And basically, that's still the table we use today.
There's antimony, arsenic, aluminum, selenium, and hydrogen and oxygen and nitrogen and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold, protactinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. There's yttrium, ytterbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver, and samarium, and bismuth, bromine, lithium, beryllium, and barium. There's holmium and helium and hafnium and erbium and phosphorus and francium and fluorine and terbium and manganese and mercurium, molybdenum, magnesium, dysprosium and scandium and cerium and cesium and lead, praseodymium and platinum, plutonium, palladium, promethium, potassium, polonium and tantalum, technetium, titanium, tellurium and cadmium and calcium and chromium and curium. There's sulfur, californium, and fermium, berkelium, and also mendelevium, einsteinium, nobelium, and argon, krypton, neon, radon, xenon, zinc, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium. These are the only ones of which the news has come to Harvard. And there may be many others, but they haven't been discovered.
Since that song was recorded in the 1950s, a few more elements have been discovered. Often we use a short form of the table, which looks like this. If the elements are arranged in order of atomic number, some interesting patterns can be picked out. For instance, these elements are all gases at room temperature. This property disappears and reappears at intervals. It seems that these properties aren't just mixed up any old way, there's a pattern. Similar patterns can be seen in the chemical properties of the elements. For instance, these elements are all metals. They conduct electricity. And these are non-metals. They don't conduct electricity. And some elements don't fit easily into either category. Now let's have another look at those elements lithium, sodium and potassium. The early pioneers knew that they all had similar properties. When the elements are arranged in order, these metals occur at regular intervals. Now that row also contains three other metals called rubidium, cesium and francium. If the pattern holds good, then they too should react with water in the same way. That was rubidium. Let's see that again. And now cesium. All the metals in this group react in a similar way with water. Mind you, the reactions aren't exactly the same. Remember how lithium at the top of the column reacted with water. But potassium, from the middle of the group, reacted more vigorously. And then there was cesium from near the bottom. These changes in reactivity going down a column are part of a pattern for the whole table. For instance, take the noble gases. There's not much chemistry to see, but there are changes in their physical properties. For instance, in their density. The noble gases are xenon, krypton, argon, neon and helium. A balloon filled with helium rises quickly. A neon-filled balloon rises slowly. An argon balloon falls slowly. Krypton is denser still, and xenon is the densest of all. Interesting patterns also occur moving across the table. For instance, all these elements react with fluorine. This is fluorine and sodium. The reaction's fairly lively. So is the reaction between magnesium and fluorine. And now aluminium powder and fluorine. This is silicon and fluorine. This is phosphorus and fluorine. And this is sulfur. It may not look it, but there is a pattern. A pattern in the formula of the compounds. In the case of sodium, one sodium atom combines with one fluorine atom. For magnesium, one atom combines with 2 of fluorine. For aluminium, it's 1 and 3. And so a pattern emerges. There is a slight problem with chlorine, but then no pattern is perfect. The periodic table is a simple yet powerful way of looking at how the elements behave, looking at their chemistry. For instance, their reactions with oxygen. Magnesium. This is aluminium burning in air. And this is phosphorus. But once more, there's no obvious pattern just from looking at the reactions. But again, there is a pattern in the formula of the compounds produced. The number of atoms of oxygen which combine with one atom of the element changes in a regular way. The periodic table helps chemists make sense of the properties of the elements, and there's an added advantage: they don't have to remember lots of facts about individual elements. The position in the table is an easy way of working out what the chemistry of an element might be. Eventually, all the gaps were filled in. But surprisingly, that's not quite the end of the story. Element 92, uranium, isn't the last. In the 1950s, scientists like Edwin McMillan at the University of California used a nuclear reactor to bombard some uranium atoms with neutrons. The result? A brand new artificial element, number 93, later called neptunium. Elements 94 to 98 were produced in the same way. (1952) saw a momentous happening, the first hydrogen bomb. A giant nuclear reaction, rather like those at the centre of stars where elements were first formed. We've come full circle, so perhaps it wasn't that surprising that elements 99 and 100 were detected in the debris of the bomb. This is modern-day alchemy, one element turning into another with enormous and frightening violence. Today, scientists have reached element number 105. There have also been claims for another 3 elements, but they've not been confirmed. What is certain is that we can predict what their properties will be in advance from their position in the periodic table.
There's antimony, arsenic, aluminum, selenium, and hydrogen and oxygen and nitrogen and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold, protactinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. There's yttrium, ytterbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver, and samarium, and bismuth, bromine, lithium, beryllium, and barium. There's holmium, and helium, and hafnium, and erbium, and phosphorus, and francium, and fluorine, and terbium, and manganese, and mercury, molybdenum, magnesium, dysprosium, and scandium, and cerium, and cesium, and lead, praseodymium, and platinum, plutonium, palladium, promethium, potassium, polonium, and tantalum, technetium, titanium, tellurium, and cadmium, and calcium, and chromium, and curium. There's sulfur, californium, and fermium, berkelium, and also mendelevium, einsteinium, nobelium, and argon, krypton, neon, radon, xenon, zinc, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium. These are the only ones of which the news has come to Harvard. And there may be many others, but they haven't been discovered.